Okay, so welcome to the lecture on mathematics of generative modeling, and we are um, working on diffusion models, and we have done a couple of classes, and we will continue to do that today as well. There is a class of generative modeling, which is so far we have done variational diffusion models, and then we have seen um, three different interpretations in the last class. And the last one was an interesting one, where, if you recall, we applied so-called Tuidy's formula, and then we saw that um, we had some kind of a score function being matched. Okay, so I will write this down again just for you to recall. And so this gives us a new class of diffusion models, which are called score-based generative modeling. Okay, so we will explicitly define what is the score. So basically, we have already formulated this in formulated this form using Tuidy's formula, but the problem is that it does not give you a good intuition behind this interpretation. Okay, so our goal will be to kind of relate things to something called energy-based models. So these energy-based models somehow give you a better view of why one should use score functions. Okay, so this is the plan for today. We will look into energy-based models, and from there we will try to interpret why score functions could be used and how we can use the denoising process. So to recall a little bit of what we did in the last class, is that we use Tuidy's formula, and using Tuidy's formula, so this is recall. So from the last class is that using Tuidy's formula, we wrote this as x naught xt plus 1 minus alpha bar grad log px divided by square root of alpha bar t. Okay, so using Tuidy's formula, we use this x naught. Okay, and with this x naught, we could write down the mu q, the mean xt x naught, and this came out to be 1 by square root of alpha t xt plus 1 minus alpha t by square root of alpha t s theta xtt. So with this Tuidy's formula, we could write down the x naught, and basically how x naught and xt are related, and from there we could write down the expressions for the mean. So this is all we did in the last class, and once we had this, then we looked at the KL divergence, because this is the term in the elbow bound. Okay, so we looked into arc min over theta of dkl, and then this is q xt minus 1 given xt x naught, and p theta of xt minus 1 xt. So this is the KL divergence we do for with this choice of the mean and so on. So then we derived this in the last class. Obviously, I'm not going to derive this. So this arg min is equal to, eventually, with this choice of our x naught. Okay, so this arg min now, it becomes 1 by 2 sigma q square t 1 minus alpha t square divided by alpha t s theta and xtt minus grad log of pxt and 2 norm squared. So with this, we have derived this in the last class, that this boils down to this expression now. And as I said in the introduction today, that this will be the so-called score function. Okay, and we have not got any intuition behind this basically we know that we apply Tudor's formula and we got x naught, and then from that we derive this. Okay, so the idea here is to relate these things to more concrete understanding based on so-called score function and so on. Okay, so in the diffusion-based model, so this is one class where this is called score-based generative modeling, and here there are like 3 references. So I should point out these 3 references. So what we are looking at a class of generative modeling which is score-based generative modeling. Yes, score-based generative modeling. So in this variational diffusion modeling, this is one class. Okay, so this is the topic for today, and the key references we are going to use is Yang, Song, and Stefano, Ermon. And this is generative modeling by estimating gradients of the data distribution. So generative modeling by estimating the gradient of the data distribution. So basically, this author Song, he had this basically 3 papers on this that more or less defines this class of problems, and another one is by the same lead author. So here and Kingma. So this and Ermon, score-based generative modeling So score-based generative modeling through stochastic differential equation. And the another one is, so it's good to note the time here. So this is 2019. So basically 1920 was, all these things were happening in 19 and 2020 during COVID time. Okay, so 2020, this guy. And then the third key reference would be again the same lead author. Improved techniques for training score-based generative models. Again 2020. Right? Sometimes you split papers like this. You have a lot of ideas. You break this into 2 papers. And this is the score-based generative model paper. And the same year he submitted improved technique. Okay, so I get to multiply your paper like that. So this is the timeline of score-based generative modeling ideas. And this is the third variant from the last class. We are looking at the last variant that we discussed, and this will be the focus of today's class. So here, this is the probability distribution at xt and log of that, but also gradient of that. Okay, so essentially what you're saying is that now I want to approximate the gradient of the log of the density. Okay, so that's the change here. I'm approximating the gradient via some parameterized neural network s theta. Okay, So that's the change. So all this relates to, although we derive this using Turing's formula, as I said, and I derived this in the last class, but the idea is more deeper than you think, okay? So it's not just mechanical formula here, but it also relates to something more deeper that people have been looking at this, so-called energy-based models, okay? So we will not go into all the detail of this energy-based model, but we will get through some of the key ideas of these models. So within this class of score-based generative modeling, we will now proceed to understand what are these score-based generative model and how practically we can compute this. Okay, so far it's in the expression right now. So hence we will do a brief review today and try to relate these ideas, and we can say that the topic is the first step in this is energy-based models. So if you want to know a lot of detail about this, then the main paper is a tutorial paper on this is missing here. But what you can do is you can do a Google search. The paper is by the author Jan LeCun. I think the title is tutorial on energy-based model. And the same guy, the King, where is that? Yeah, here, right? So this guy is was the one behind variational autoencoder, if you recall, and various derivations of that. But then he had another paper. So how you train energy-based model. So I don't know all the author, but I think this is the lead author. So how do you train energy-based models? Of course, I have not defined what this is, but these are the references. This is the main reference if one wants to know a lot more about that, but our focus is on generative modeling, so we will just know enough which is helping us in the generative modeling. Okay, so the idea of the energy-based model. Okay, now I see. So so I mean, this is the tutorial, but the original author is cited. Well, the original paper was like the original idea, let's say, okay, and then this tutorial kind of expanded on that, and then they said, look, you can try this on many different. You can see many of the machine learning tasks as kind of within the energy minimization framework, okay, something like that. So you can see regression problem also like that. So there's many type of problem could be seen with this view. So of course we won't go into all those. So the initial idea was indeed by Hinton, which is referred here, idea of, but I usually read this energy-based model. This is by Hinton. Is a big shot guy, in case you don't know. Okay, we got Turing Award, and he's one of the key persons behind most of the machine learning revolutions you can think of, especially deep learning. So, for instance, how to train a neural network was one of the challenging problem. Basically, we train neural network via gradient descent, but then computing gradient of these complicated networks was not very trivial, okay, with a lot of parameters. So backpropagation is a way to compute the gradients of a neural network. This is denoted by f theta, and this was a major bottleneck because neural networks as such were known a long time ago. I don't exactly remember the timeline, but more than 50 years ago also. But then the problem was, if I'm using gradient descent, then I didn't know how to compute efficiently. Okay, I can always compute, but how do you compute in a way that it's tractable? So although the backpropagation idea was proposed by someone else, Hinton showed that this can be applied here as well. Okay, so that's the topic of machine learning course. So and even in our case, we don't even bother. So the point is, this is about energy-based model, and this refers to Hinton, and he did some other kind of work as well. So So idea goes to Hinton, and the basic idea is the following. So so the basic idea is the following. Basic idea or motivation, whatever you can say, okay, is that rather than explicitly learning a probability distribution, a probabilistic model, let us say p theta over space x, instead learn an energy function, right? So that's what I said. Many of the machine learning problems could be formulated as a probabilistic model, okay? Even think of linear regression and so on, okay? So so if there are probabilistic models, and obviously there will be some theta and so on, then instead of learning that probability model, learn so-called energy of that, okay? So learn an energy functional let us say denoted by E theta, and that goes from x to r, so it's like real valued. And once I learn this, then I may use this to estimate the probability model p theta. And in fact, some of this we have done already without even mentioning energy functional. So when we were doing generative modeling using optimal transport, then there was a time when we used something similar. We defined some E type function, and then we normalized it, okay, and the name given was Gibbs distribution, okay. So this is something we have seen. So that's the same Gibbs distribution we will be talking about. So I will learn E theta, okay, which is the so-called energy functional. How we define and so on, it's something we will see. And this energy functional can be used to estimate the probability, okay. So can be used to implicitly define a probability distribution. For example, a Gibbs distribution, right? Okay, so this is p theta x is 1 by z theta e to the minus e theta x, and where z theta is the integral of e to the minus e theta x, basically a normalizing expression, right? So as I said also previously, we can define distributions as long as the values are non-negative and their sum is 1. So if I take an integral of this, so any function defines a PDF if it takes non-negative values and the integral is 1. Okay, these are the two things you require. So not going into details of measures and so on. So these are the basic things you need. So in this case, we satisfy that. This takes positive values, and if I integrate, then the numerator denominator is already integral form, so they get cancelled and we get 1. Okay, so this is a way to define a probability distribution. Okay, so what might happen now is that rather than learning this, you want to learn this. Okay, but then there are many questions here. Now, what will you do with z theta, right? So, okay, so let's see. So for the moment, we can write p theta like this. Okay, so the problem here could be when, so it's easy to construct e theta x. In general, I can construct, but it may be difficult to estimate z theta. Okay, but challenging to enforce the constraint p theta x equals to 1. So if we want to go via this route, which is estimating the density function via the energy E theta, then we have two major problems. So need to solve two problems at least. So the first problem is we need a training procedure to optimize the parameters of the energy function. So the first one is need a training procedure for optimizing the parameters of the energy function E theta. Obviously, we need to train because E theta is parameterized as theta, and so that it obviously like approximates so that so E theta defines a probability distribution P theta, and ultimately we want P theta to be close to the original distribution P. So that the implicit distribution P theta approximates the data generating distribution Px. This is the first problem we have in hand, how we will train so that the implicit distribution will be close to the original distribution. And the second one is we need a sampling procedure to draw samples. Okay, so once I have the P theta, then let's say I have learned a generative model P theta, then the question is how should I sample from this distribution, given that I know E theta and I don't want to compute Z theta because Z theta is challenging. Okay, so it's challenging to enforce calculate Z theta, and but yet I want to sample. So the second problem, we need a sampling procedure for drawing samples x P theta, obviously. So, and as I said, sampling is not easy because even if you learn this to sample, you need this also. So what will you do? Okay, first thing is to train E theta so that the implicit distribution will be P theta will be close to the original distribution Px. And second is, even if I know that I have implicitly learned, how will I sample? So these are the challenges for energy based models and specifically for generative models. So solution to both the problems should avoid, as I said, computing Z theta. Okay, so solutions, any solutions that you come up with, so solutions should avoid computing Z theta. Okay, so these are the two challenges you have, and then you have to build a way to compute P theta, which is close to Px. So let us keep aside the first one for the moment, where we are supposed to know how to train E theta. Let us look into the second one first. Okay, so looking at 2. So looking at 2, basically it's about sampling. So someone gives me E theta and then tells me, can you give me some samples? So there are some connections with so-called stochastic differential equation, and I'm not supposed to kind of do the detail. I'm planning to make a separate video on SDE, but today we will just know the technique. Okay, how it can be used. So So basically we want to, so looking at the two, we want to sample, let us say denote that sample by x, okay, usually the case, and we are sampling from this, which is an implied distribution. We call it implied because the first step is E theta, and then from there P theta is implied. We want to sample x from P theta. So directly sampling from P theta is difficult. Okay, so that we know. So directly, I'm kind of rewriting the directly sampling from P theta is difficult. Okay. So what we'll do, we will take some advantage from these areas where people study Markov processes. Continuous variant of Markov process is an SDE. So we will leverage those developments. So we can approximate samples. So can approximate, okay, without going into too much detail. Okay, I will plan to kind of make separate thing. Okay, in this course it will do too much. So we can approximate samples using Markov chain with stationary distribution the stationary distribution we take as P theta. In fact, this is how we will kind of go there. Okay, so we define this so we define first a continuous variant of Markov process. So continuous Markov process would be differential equation basically. So as I said, we don't want to know the differential equation part, but what we want to know is the algorithm that will be used. Okay, so okay, so we have the continuous variant, which is del xt by del t plus grad x log of p theta xt dt plus square root of 2 dwt, where dwt is some noise. Okay, let's say Gaussian noise, and so a diffusion process that follows these dynamics. So the result we have is that a diffusion following these dynamics converges asymptotically to the samples x. And by convergence we mean, because these are kind of stochastic, so by convergence we mean under some probability measures that is well defined for comparing, right? So this means that the KL divergence is xt and p theta tends to 0 as t tends to infinity. So the solutions of the stochastic differential equation converges to p theta. Okay, so again, I'm not going to do a proof of this. Okay, so proof is skipped. I can do this separately. So this, we take this as a result that if I can solve this differential equations, obviously there will be 0 here. It's an equation. So if I solve this, then and obviously it's a time. There is a time component involved, and usually you will use an iterative method. Okay, that's how you solve time dependent, unless you have some direct closed form formula to integrate out everything with time. Usually you won't be able to do. So you will do this by iterative process. You will partition the time steps as t0, t1, tn, okay, and then you get x0, x1, x2. So hence it's an iterative process, and this is what it's trying to say, that during this iterative process, as you go more and more in time, then the sequence that xt, x1, x0, x1, x2 you are producing will eventually converge. Okay, so now numerically it depends on you to determine when to stop. So basically numerical computing area, we stop at a point where we are happy with the accuracy and so on. So even with the normal ODE that you may have seen, you know how to kind of approximate this. It's a time derivative, so I can do some finite differencing here, and so the idea is to what would be the discrete case, and how will I get these xi's. So we look into the discrete variant. So we know that we can discretize this. So discretizing. So let us call this as equation diff, okay, diffusion equation. So if we discretize, then we can approximate a derivative by doing the finite difference. So xt plus 1 minus xt by t, okay, something like that. So this is the approximation of the derivative, and that's it. And then from there we will write xt plus 1 in terms of xt. So if we do that, then we have, so basically xt plus 1 minus xt by, let us say, the time difference, right? The interval we are solving a ODE, t0, t1, t2, and so on. And let us say this is a uniform partition of the time. Then each distance between each of these, let us say, is eta, I guess. It's taken to be eta, okay, and it's a uniform, so all are on eta. So with this, the time difference between these two time is eta. So this must be equal to everything goes on the right hand side, I guess, and we make it negative. So this is equal to minus log of p theta xt. Okay, no minus 4 epsilon t, right? Okay, so this is minus square root t2 d wt. Okay, and we will assume that this white noise wt, as I said in the beginning, is some standard normal. Okay, so let us say that this white noise is taken from, it's some epsilon. Okay, and this epsilon is noise is basically some random variable coming from some distribution. So let us say in this case is epsilon coming from standard normal. So I will replace this by this guy here, and then in the continuous case, I mean discrete case, I have xt, and then minus eta and plus square root of t eta epsilon t. And these d terms go away in the discrete case. So this is the update rule we have. Okay, in the discrete case, I will update xt plus 1 from the old xt and these. This is analog of the Euler discretization that you may have seen, analogous to Euler scheme. Okay, in ODE you may have seen this. Okay, so what we are interested in is this. We mostly deal with the discrete case. So coming back, our goal to use this is that the solutions to this xt gets closer to p theta, which is the generative approximation of the generative model that we are trying to learn. And as t tends to infinity, that happens, and then we know a way to like produce these xt plus 1. Okay, so this is obviously approximation of the continuous, because eta is a discrete. We are trying to approximate a continuous case with the discrete, right? So obviously we are, continuous means that you take everything, right? But here we are taking eta here, right? So the only way this derivative becomes equals to that derivative is when t tends to basically 0. Okay, so we define the derivatives like that. of this f at x is, we are trying to do that, and in our case, in place of t we have eta, and derivative in place of x we have t, and hence this is the, so the only way this discrete becomes closer and closer to the continuous variant is when t is close to 0. I mean eta is close to 0. So and this is also like all this is called Langevin dynamics and Langevin dynamics and so on, but okay, let us skip that for the moment. And so now we go to the score matching that we had in the beginning, and in the score matching we are supposed to kind of look into this. This is the s theta that we're thinking of. So score matching. So we go back to the expressions that we had relating p theta and e theta. So p theta x is 1 by z theta e to the minus e theta x. So this is what we have. So we want to relate, right? So what we have in hand is the log p theta, right? And that kind of relates, I mean log p theta, and then this guy will show up here, right? So let us go back to that. So this implies grad x log p theta x is equal to minus grad x e theta x minus grad x log z theta. So p theta grad, we took gradient with respect to x, but first we took log of everything, and then on top of that we took gradient, and that's what we have. Now what will be the last term, right? Last term is not a function of x, so that drops because we're taking gradient with x, but the last term is z theta, so that drops, and we are left with okay. And as we started in the beginning, and also we saw in the last class, is that we may want to use something called a score function, right, s theta, to approximate this. Okay, so essentially what we may want to minimize, so we will denote this basically by, not estimate, okay, sorry, denote this by s theta, and what we want in practice is that this s theta is equal to log px. That's the original distribution. Okay, so and we know that this is related to energy function also. Okay, so what we want is that log p theta is close to log p x. That's when we will say that okay, the p theta has learned. But we also know that p theta is now also related to the energy function. Okay, these are the connections we see now. Okay, so let us use a so-called score function. So define a score function like this: s from rd to rd, right, by x to grad x log px. So score function could mean grad x log px, but score function could also mean grad x log p theta x, depends. So basically in general, score function is like take gradient of whatever density you are giving me. In this case density is px, then the score function is grad x log px. If the density is p theta x, then the score function becomes s theta. Okay, we will use a different notation for that. So we want to estimate this score, want to estimate this score by neural network. Okay, so neural network s theta, right, which goes from also rd to r, rd to rd, and which implicitly also is related, right? So which implicitly defines an energy function, in our case is e theta. Okay, basically you have to take a integration again, right, because score function is this guy, right, but then to explicitly solve for e theta you have to integrate over x so that this gradient gets cancelled, this gradient gets cancelled, and then you, from the score function, you get E theta. So now we will define we know what is a score function. Basically, it's gradient of log of some density, okay? Some density at a point x, okay? And gradient is with respect to x. So x is a data point, right? So samples. So let us define some optimization problem, because now it is more or less clear that there will be some score function. This score function will be this, and we want this score function to be close to px. So we want s theta to be close to s. That's when we will say that p theta has learned, okay, and it's similar to px. So basically, we will define an optimization problem now, saying that minimize s theta and s. Obviously, in the optimization problem, s is not known. So that's where we will further discuss what we will do to solve this optimization problem, where s obviously is not known because p is not known. In fact, this is what we are trying to learn, right? So first we will define a minimization problem. So we focus now on learning this score function, which in our case is s theta, and that minimizes. So before we started learning, we always have to pose an optimization problem, right? So s theta, that minimizes the so-called Fisher divergence. So I will explain what Fisher divergence means. It's nothing but just the log of the original, I mean, kind of log of KL, but okay, we will define it anyway. So that minimizes the so-called Fisher divergence, which we define immediately, okay? The Fisher, okay, there is no C, okay? And sometimes I make mistake. F-I-S-H-E-R, F-I-S-H-E-R, okay, Fisher divergence. So which is defined as follows. Expectation of x from density p, half of norm of, so this is like L2 norm we are defining as an objective of this optimization problem. So log px. Okay, so we want to learn s theta, and to learn something we first need to know what is something to learn. We want to know what is to minimize or maximize. That's what it means. So this is what, if we minimize, we will say that we have learned theta, right? So I mean, I have not yet defined. I did not define the. I mean, I encoded the minimization problem in words that I want to minimize this. But furthermore, I could have written minimize theta for this guy. And so the Fisher divergence is another kind of a measure that that I will define it as a separate thing. So Fisher divergence is defined as d Fisher and p. So since it's a probability divergence, so obviously these are densities. Half of grad x log of px by qx. As you can see, this is KL. Okay. So this is KL divergence, but log is, I mean, not log was already there. The gradient is there. Okay. So it's like gradient is somehow inserted, right? So it's analogous to KL was log p by q, expectation over p. But Fisher is like we have this additional term there. So this is analogous to KL. Since we are looking into the gradients of the log densities, that's why we now would prefer to use Fisher, because Fisher indeed deals with the gradient. Okay, there is a lot of thing about Fisher. Okay, if I am doing a maximum log likelihood estimate, right, MLE estimate, then the way I will maximize is an optimization problem, and one of the ideas is that you work with something called a Fisher matrix. So take a derivative of the log likelihood, take outer product, and then use a gradient descent with that as an approximation of the Hessian. Okay, So that's called natural gradient descent. So that thing comes up in optimization method, but it's a natural. So there is also a connection from there, okay? Natural gradient method. So basically this is a kind of a approximate second order method where the Hessian is approximated via the gradient of the log probabilities. Okay, so there is some connections with the optimization as well, but let us skip that. So we have defined the feature. So basically we have one more in our kitty right now, that I also have yet another divergence measure. And how they are connected with the KL, there is one more result, but I think we don't need it for the moment. Okay, so I will skip that. So how it's related to the KL and so on. So, but I will just state that theorem. Okay. So basically, we will take a derivative of the KL, and it's related to Fisher. Okay. So this is by LYU 2012. So under mild conditions, d by dt of dpt qt minus dpt qt. Okay, so what we are saying here is that so here we change the derivative notation to t rather than x here, but what we are saying here is that derivative of the KL is negative of the Fisher distance. Okay. So, but we will not prove this. So, if you want to prove see the proof, you can go to this reference. Okay. So now we can come back to the problem that okay, we have posed a optimization problem, and we are supposed to learn the score. This score will eventually give me the energy and so on, right? That's what energy-based models need. Okay. So so this score function that we have is basically this is not tractable in the optimization problem. So it's a challenge now that how will I really find a theta for which this is minimized. Okay, I want to minimize this. So the next set of results that we will see will until the end of the class is will be about finding this theta, a tractable way to solve this problem. Okay. So then we go. So this is called score matching problem. So then we look into this now, and we use a set of results to see what we can do with this. So implicit score matching. Yeah. So I already said that. I'm not going to repeat the. So we will use this proposition which is called implicit score matching, and this is by it's hard to pronounce this name, Hivarinen 2005. Okay, so this result was proved there, and basically the whole idea is to make these objectives tractable. So the result says that arg min of theta, expectation of x from P is half norm of s theta x, which is what exactly is what we have written, and this is the left hand side right now. So grad x log px is equal to arg min of theta, expectation x p, and this is trace of grad x s theta x plus half of norm of s theta x squared. Okay, so so the left hand side, which is kind of not tractable, is now we have to see whether the right hand side is good for us. It's in the form of s theta. It seems like everything boils down to s theta now. Okay, so log px has disappeared. Okay, so and s theta we have. Okay, so of course it is still a minimization problem, but what is good now is that at least I know what to evaluate. Even if I'm using some gradient method or something like that, I need to know what is the function and whether the function value is decreasing, increasing, and so on. And so at least that is there. Here, I had no idea how to evaluate the objective itself because P is not in my hand. So at least the right hand side is giving us some way to evaluate the objectives and then optimize for theta. Okay. So let us try to do the proof of this. So the left hand side we will start, and it's on the of the form a minus b whole square. So we will expand that, and let's see what we will get after expanding. And in fact, we can drop the constant term. Which will be the constant term? It will be the one with only x, because the optimization problem is with theta, and that's more or less giving us intuition how that term got dropped, because that was only with x, and that was playing a role of a constant. So when I am minimizing, then minimization of an objective argmin is same as the argmin of that objective without the constant. So let us do that. So this is argmin, but it's not just that we have to go until there, right? So that's the funny part. Is just dropping is not enough. As you can see, there are trays and so on, right? Okay, so this is argmin theta. So yeah, basically I'm going to repeat this as in the notes. So okay, let me do that. So this is again the left hand side half of norm of s theta x minus grad x log of px, and this is equal to argmin theta so when we will expand, there will be 2ab term, right? So a square minus 2ab, a b square I drop. Okay, I mean I'm going to drop. So this is a squared, the half remains outside, so no square there. So a square minus 2ab minus, so this is minus 2 s theta x, and then grad x log px, and plus, okay, therefore as a first step, let us also include this guy, which is going to be dropped, log px squared, and expectation bracket close. So as grad x log px is independent of theta, we drop it. So this becomes argmin theta expectation over x of half s theta x minus 2 s theta x grad x log px, and norm squared. And I believe half should have applied to everything. So but it's taken care of. No, not now. Now it's not taken care of because this, okay. But then we remove this, right? We just remove this too and let it be with the first term. Okay, so this is the simplification we have right now. And what are we going to do next? So if we compare with the original term, it seems that the difference seems to be just this guy. Okay, so if I have to prove that they are equal, then this term is already there. Okay, so what we are left with is that other guy should be norm of s theta squared. Okay, so this is and then I mean the other guy is half of the s theta is already there. What we are supposed to prove is that this guy is the trace of grad x s theta. This inner product is trace of grad x s theta, then we will be done, right? So yeah, so basically we now look into this, and this is an expectation, so we can also take it inside, so that's fine. So so let us look into this term now right now. So we just need to show that the inner product term is equivalent to trace of grad x s theta x. So this is an expectation, so then we will have integral, and there will be a small exercise in that. I will leave that for you. So let us say this is, we have to recall integration by parts now. So this is s theta x transpose grad x log px. So this is where we start with, and this is equal to sum of I equals 1 to d, because this s theta and all are d-dimensional vector. So if you multiply this, then we get a sum of d terms pointwise. So there is like ith with ith entry of this, and this is a sum over I equal 1 to d. So this is what we are going to do now. So I equal 1 to d, and then for each of these, expectation will go inside for each of the ith term. So ith term of this and ith term of this, and integration of that, right? So expectation of that will be the integral. So this is x s theta x, and we denote that term by sub I, and log of px by del xi px dx. Okay, I hope you agree with this. Ith term of s theta and ith derivative of the log px. Okay, basically picking the ith term of this is like this, because with respect to the other I, it will be 0 anyway. So basically I don't have to write the ith term of log p. Just taking derivative of the ith will give me the, will look at the ith term itself, because other will be constant. So that seems fine. And since this is an expectation, so I have to put the PDF p here, right? So we are just trying to recall this basic stuff. Okay, so a natural thing to do at this stage will be basically the del x by del p, the pp gets cancelled, I believe, because del x by this of p will be 1 by p, and there is a p already there. So 1 by p, p derivative, because there is a log. So one of that will get cancelled, and that's the derivative of p will remain. Okay, so that's the further simplification we have. So I equal 1 to d, and then integral of s theta x, the ith term of that, and then as I said, derivative of log p 1 by px times del by del x I of px, and then you have px here, dx here, this px gets cancelled, and then we are left with sum of I equals 1 to d, and then this is integral of s theta x and del by del xi of px dx. Now we will use integration by parts, and when we use these are integral over all over x, right? If I do integral over parts, then we will be left with only the term which is the negative one, I equal 1 to d, and integral over x s theta x dx. So the exercise that I said is to figure out why did I drop one of the terms. Okay, I will write only one term here. So I say that this is this, but when you do the integration by parts, fx integral of gx, okay, minus integral of differentiation fx plus gx, but I said one of them will drop. Okay, so exercise y other term was 0. Why is that? So we have this simplification here where so how should we, I mean, so our goal was to go up to trace, right? So do we see that it's a trace? It is indeed a trace, right? Because trace, you see there is only II term left, I mean II term of this guy, right? So it's like summing up the diagonal of s theta, right? So if I take a gradient of s theta, okay, and then so take the gradient of s theta and with respect to x, and only look at the diagonal entry. Okay, so so I hope you are able to figure this out or not. Okay, so should I write this, or basically should I write this, or should we? This we claim is the trace. Basically, it's a notation thing, right? How should I look at this, right? So what I'm saying is that I see this as a trace. So this is trace minus of integral of trace of grad x s theta x px dx. In fact, I can also leave this as an exercise, right? Right. So trace is sum of the diagonal entry. So I just look at the II term, right? Even if I'm taking derivative, let us say if I'm taking gradient, right? So gradient of x of s theta. S theta was from where to where? What was the nature of S theta, right? That we need to know. Nature in the sense like which domain to which codomain, right? So what was that? S. RD to RD. Is that correct? Right? RD to RD, right? So S is RD to RD, and we are computing gradient. So what will the gradient of a RD to RD function, right? I remember it's RD, just double check, right? So define, yeah, RD to RD. And what will happen if you take the gradient of an RD to RD function, right? So S theta goes from RD to RD, and I'm supposed to compute the gradient of this. And with respect to x, x is of course also RD, because I mean from here itself we know that the domain quantities are RD. So this will be d by d matrix, right? So this will be, it's a calculus thing, right? So S del by del x1 S theta x, okay, and then del by del x2 S theta x, and so on, okay. And then the point here is that these guys also I have to kind of like denote it in the form of 1, 2, 3 and so on, okay. So I can, okay, if I'm indulging in this, then let us do that. So S theta x is S theta 1 of x, S theta 2 of x, S theta d of x. Grad x S theta x is del by del x1 S theta 1 of x, del by del x and S theta n of x, or d of x, d of x, and del by del xn S theta not n d, d of x, and del by del xd s d theta of x. And what we are looking at is that this expression here is, these guys are being summed over. So basically I'm looking at this diagonal term, which I define it to be the trace. Take trace, so basically take trace, and I get the del by del xi s theta I. Okay, so if you want to exactly denote by that, then this is sub, okay, this is d here, this is 1 here, 2 here, d here, okay. So maybe you can think of this as, so you also do this as an exercise, as a clean thing, okay. So homework exercise. Okay, so we know that this is trace of this and times px, okay, and that's it. This is there was more, or that's it, I guess. So this is, but you just write this as an expectation now, expectation over this, right? So this is expectation of, and all this is negative, so negative of expectation of xp, and then trace of grad x s theta x, right? 2 exercises, try to fill those calculus exercises. Now we move to sliced score matching, and so the problem here is that we cannot stop even with this, because the problem is, let me write this down. So you can say, is this already computable, then why are you going more on this? Basically this s theta trace and all this will be more like still we can like improve on that. That's what I'm trying to say. I mean, you can compute this, but can we do better? That's the point. So then there is an idea called sliced score matching, and this is the same guy, Yang, okay, the lead author that I referred to in the first 3 references in the beginning. sliced score matching. So before that, I will like motivate why I do that, right? So what we have is that the reduced optimization problem we have is this, with trace of grad x s theta x half of norm of s theta x. So what we have said is that score matching and minimization of the theta boils down to this. And what we said is the previous one was not tractable. This is tractable in the sense that at least I can compute this, but maybe it's maybe we can improve further on this. So that's the goal of the next this topic called sliced score matching. And here the sliced score matching would refer to kind of sometimes if original problem is difficult, you may want to project that problem into a smaller dimensional space where it is cheaper to compute. Okay, so that's the main idea of this sliced score matching. So this, but before that, some remarks on this. So this can be approximated by Monte Carlo. Okay, basically we are supposed to compute expectation of this guy. So Monte Carlo says that approximate that quantity over some samples. That's what Monte Carlo means, right? So samples we will have a lot of cat images, whatever, right? And so that's the good thing about machine learning, right? So you are given some samples, so some quantities, if it's like this, you can always approximate over the samples. So in that sense, we can compute this, although it will be still an approximation, but it can be done. So this can be approximated Monte Carlo and evaluation of the objective. So let me put this as the next point. So evaluation only involves s theta, but it is still not yet convenient because of the high computational cost involved in calculating these terms. So this is not yet convenient because trace of grad x s theta x is a second order statistics. Okay, second order statistics means second order terms are involved, right? So second order statistics because it is the trace of the, remember that it's a trace of the Hessian of the p theta, right? So it's worth noting all these points, right? So it is the trace of the Hessian of log likelihood p theta x. So this paper, sliced score matching, went ahead to give a cheaper way to compute this. And as I said, the idea was to project this into some smaller dimension. So introduce some random projections. So example from the Gaussian standard normal. So we'll try to project this on some Gaussian random vectors. So this will be L theta v now. So it's a projected objective. Okay, so what we have done here is that we have applied a projections, right? So if you are given a matrix A, then projections of a matrix A on a vector V is like denoted by this. Okay, so these are kind of projections. What I'm doing is like I'm making them go on a smaller dimensional space because this s theta is a d-dimensional space, but after multiplying with this, it becomes one-dimensional, right? So SD x will be d-dimensional. V, I believe, will be also defined to be obviously to have a inner product, it should be, let us say this is also, and there is no such notation like this. So let us say this is D. So inner product of D with D will give me just a number. Okay, and that's that seems to be cheaper, right? Because there you had S. This is a matrix. I mean, S was a vector, but then after taking that trace, I mean, after taking the gradient, it becomes a matrix. Okay, so this is what we are trying to think of right now. Is, I mean, we started from the original equation, right? If you recall, the original equation was S theta minus. So let me write down. Okay, so this is a projected version of expectation of xp half s theta x minus, and this was a norm grad x log px. So this was our original objective. If you can recall, we are doing a score matching where s theta must match the original distribution, and this is the projected variant where just the new thing is v, and since this becomes a number, I remove the norm because these are two numbers now. So I just take a square basically. So this is a parenthesis here. So I just look at the square, I remove the norm there. So we are now we want to look at the projected variant, and so the next step here is, yeah, so this is just the loss right now, and we want to look at the argmin of this, right? So we want to minimize this. So we'll do a couple of steps. Usually the ideas are taken from optimization. That's why optimization course becomes a very important course. So we are supposed to do argmin of that, and but we will do some simplification of that. So I'm trying to figure out what is a good way to do this. So I'm supposed to do argmin of this projected one, but the way I will see this is minimization of a quadratic, let's say. Okay, there are these equivalences between them. Okay, so what I will do is that I will write down, and then I will show why is the case, right? So argmin of theta and expectation of v r l theta v is argmin theta expectation of v transpose expectation of So the point here is like, does this make sense to you, right? So is this the same as that? And the difference there you see is there is one v there. Right? So there is some v there, and the point here is that the argmin of this, why should it be this? So let us see this square term, right? That's one way. I'm not sure. S theta x minus v transpose grad x log of px, right? Yeah. So they don't show this details here. So let's see, we just multiply this, right? So this is log px, and then we close this, and then v transpose s theta x minus v transpose grad x log px. We get a v transpose from the right as well, but that v transpose is with s theta. That's fine, because both are kind of numbers, right? So this is v transpose s theta x, v transpose s theta x minus v transpose s theta x, and then v transpose grad x log px, and then minus v transpose grad x log px. Basically this is like minus 2 times of that. Okay, so this is like minus 2 times of that, and then plus of v transpose grad x log px, and then v transpose grad x. I mean, I am writing squares explicitly as repeated terms just to see if there is a connection there. So this is like 2. So do we see this, right? So so we may have to also expand the inner one, I mean the norm one there. So if we expand the norm one, then what do we have, right? We have norm of s theta x squared, but I don't know how it will relate to this. So let us say I expand that, right? So this is s theta norm of s theta x which will be, so since everything is in transpose dot product form, let us say this norm of s theta square is s theta x times s theta x, okay, and then plus the second term is grad x log px transpose grad x log px. So that's the second term, and then the third term is minus 2 s theta x transpose grad x log px, okay, and then there is a v multiplied on both sides of these, right? So in this case we have v transpose v, and then there is v transpose v, and then we have here v transpose v, and we are kind of saying that when I do minimization of this over theta is same as minimization of this over theta, okay, that's what you're trying to track, and these two are like matching like that, and this guy, I mean not yet, but we're trying to relate, right? So the first term, like, is this correct, right? S theta is the same as this. It looks very close, but not sure they are same. Minus 2 v transpose s theta x transpose grad x log px v. All the terms are there, but can we say they are equal? What do you think? This is sometimes inner product view also helps. So this is let us say this is a transpose going on for this guy, right? So we, let us say we define inner product as y transpose x, okay, so the transpose guy, let us say we put it here, so this is like s theta transpose v, okay, and then when I do transpose there will be v s theta, and this gets multiplied with v theta s theta. So this guy is this, and then if I look into this guy, then this guy is v, let us say this is v, and because the transpose if I take then it will come that side, right? So this is like v transpose s theta times v transpose s theta, that's right. And here if I do, so basically this transpose should come here, so v, and let us say this is s theta x v, okay, and here we put s theta transpose x v. This is, these two are this inner product same, right? So s v transpose s theta transpose v, that's right, and then this is v transpose s theta times v transpose s theta, right? So the question is, are these two inner products same, right? That's another way to look into this. Inner products are symmetric, so one thing I can do is that I can send this guy there, so at least this guy matches, okay? So let us say if we do that, then if we interchange this, then what we can at least say is s theta x v and s theta transpose x v. So at least this is matching, but then it must be that they should match, right? Why is that, right? So v transpose s theta must match s theta v, but so far we don't know why it should be the case, any condition on s theta that makes it like this, or even for symmetric I forget the symmetry because s theta is a vector here. So all right, this is a rho times vector, and this is even the dimensions look very strange here to me, because this let us say vectors are like, let us say columns, so this will be rho, this is a dot product, but this guy like this is outer product. How is this possible? This is looking a bit strange. I mean, point is like these guys are number, so that's fine, okay, we can multiply, but then this is not possible, right? How is this possible? This is rho times rho, so something is missing, right? Or maybe I have done a mistake there. Yeah, obviously we have done a mistake there, right, I can see. So that was norm of s theta squared, right? So that was norm of s theta squared, so how can both be transposed, right? So this is, one is like transpose, other is not. Right? So norm is like x transpose x, so this is like this. I may have done similar mistakes. Now here I've done fine, right? X transpose X form. So here there was no transpose, right? So if there was no transpose, what does this mean, right? So we can go back to this. So we first one was this, and second one was X transpose. So this is there, and then V transpose S theta transpose times. I mean, you see, this is a number, right? Okay, so what I can do is I can do S theta transpose V. Okay, so from here to here, so this is same as S theta transpose V, right? Because X transpose Y is Y transpose X, right? So V transpose S theta is S theta transpose V. So what we have is S theta transpose, and what we have is S theta transpose S theta. So now the question is about whether S theta transpose is same as S theta transpose S theta, right? Perhaps it holds. Okay, if A is symmetric, then it will be holding. It will hold because this is transpose of this, right? So here we are assuming that S theta is symmetric. Okay, usually it happens that these guys are symmetric. So if that is the case, then we have that. Okay, so at least the first term we have that, and these guys also we have to have the same argument that these are symmetric basically. Okay, right. So it seems to be okay. So and then this guy, the similar argument holds that we say that this is symmetric. So that's why this guy is equal to this guy. And then the middle term -2 term we have to see. Okay. Okay. In that case, we have to say the product would be symmetric, which will be a very strong claim, I believe. So if you look at the second term here, what we are saying is that V transpose S naught X, and then V transpose grad X log Px. So what we are saying is this is equal to V transpose S naught X transpose, and then grad X log Px. Right, so grad X log Px, and then the V is outside here, and V transpose S naught X transpose, right? So what we're saying now is that this holds. Again, we can do the same trick. This can be flipped, but then when we flip it, this will be transposed there. So let us do this one step to convince. So S naught X, V transpose this can be flipped, but then it will bring a transpose for this guy. So grad X log Px transpose V. Okay. So now our question is, these guys are same. Okay. Okay, now everything depends on the symmetry of this. So for these guys to match, so need grad X log Px to be symmetric. Okay, so I believe that all this is the case. Okay, although we have not done the additional checking that these guys are indeed, but then the distributions we are looking at, I believe, should be the one which have this property that these are symmetric. Okay, so if and usually it will be. Okay, so then being symmetric, everything holds. And then the previous case S naught X being S naught X transpose X being symmetric also, we can flip. Okay, so with this we can say that okay, this this minimization is okay. Okay, earlier I had some other thought from optimization, but that's not the case. Okay, I was like thinking somewhere else, something else. Okay, so this way we have to prove term by term, and it seems to hold. Okay, so that was so, and then yeah, there are two more lines, and then we can stop with this. So the next step is, yeah, so basically the trick was nice, because then we took this V out, and we had this form now. And then so basically we started with projections, and projection problem we reduced to something which we are familiar in this norm form. And but then within this norm we will get that trace term and so on. A trace term is difficult, but then now they are projected by V. So overall, it will boil down to, in fact, a number, because outside V is there. Even if it's a matrix or whatever, the whole thing will be a number, right? So that was the trick, that we took the V out, and now we have like 2 more lines. So this is equal to argmin. Okay, so yeah, so let us start with argmin now. We have not introduced argmin yet. So this is expectation of V R L theta V, and this is equal to argmin over theta of expectation of V R V transpose expectation of X, and then half of S theta X minus grad X log Px. Okay. So we have done that derivation, and we are here right now. I just copied over here. And what we know is that we did some simplification of this as a first proposition we had, and this boils down to argmin of theta, expectation of V R xp V transpose grad X S theta X V plus half V transpose S theta X squared. So this is from the first proposition, right? This is from the proposition that we had before. So good thing about this objective, right, compared to the previous objective, is that now it's a Hessian vector product. Okay, so that's simpler, right? Matrix times vector is simpler than some matrix operations, right? So hence it becomes easier, okay, where I just need matrix times vector product here. So this involves only Hessian vector product. Okay, so where are we? Okay, okay. So 2 hours, right? Actually, there was just one proposition left, just like 4 lines, and this notes could be done. Later? Okay, let us stop then. Okay.